When I walked in, one of the big concerns we had was that China and Russia were making great advances in this field. And we, the United States, had allowed our lead to slip. In fact, by any metric that I could construct, we had fallen behind our peer competitors. The story of hypersonics is really, in many ways, a frustrating one because it's a field that the United States invented. We did all the foundational work. We developed the concepts. We did the early experiments. We had the early successes. And then we took our foot off the gas. We backed off from investments and we let peer competitors like Russia and China advance to the point where now they're ahead of us in this field. My number one job was to make these principal directors successful. That's the job of a leader, make the folks in your organization successful. And if you look at some of the mistakes that I think we made, one was we allowed our test infrastructure to languish. We shut down wind tunnels. We stopped using wind tunnels. I'm happy to say that there have been significant investments in both those areas.
So Mark, thanks a bunch for joining us here on the Microjourneys podcast. It's exciting to be here in Washington, D.C., and great to catch up with you again. You and I had the ability to work together when we were over at OSD, Office of Secretary of Defense, but you have quite a bit of accolades that range from a variety of different areas, both on the industry side, academic side, government side. Would be very curious to understand what helped your career path before you got into the to the Pentagon that really kind of stands out as a critical moment in your life.
So first, thanks for having me. I'm really looking forward to this conversation. And you know, first I'd say is I have had a relatively non-traditional career, and I'll explain that. When I first finished up graduate school, I started working as a faculty member, and that was my career plan. I was going to be a faculty member for life, go through the academic ranks, assistant, associate, full professor, make sure I was going to get tenure, and then I was going to, lecture until I died at the podium. And really, the kind of the seminal event in my career was being asked to join the U.S. Air Force's Scientific Advisory Board. And that was in the late 1990s. And a little bit of background on that board. So as you probably know, the United States Air Force came out of the United States Army. It was the U.S. Army Air Corps. And towards the end of World War II, you had a number of leaders who decided that there needed to be a separate Air Force. One of those was a man named Hap Arnold, who was the general who oversaw the U.S. Army Air Corps in Europe. And Arnold is often considered the father of the U.S. Air Force. So as he was thinking about forming this new fledgling service that became the Air Force, he wanted to have connections to the scientific and engineering communities. And so he created what was known as, at the time, as the Scientific Advisory Group, which still exists today as the Air Force Scientific Advisory Board. Really long history. If you look back at people who've been on that board, it's an amazing who's who in defense science technology. So in the late 90s, I was asked to join the board. And to me, that was such an eye-opening experience. The Air Force knows how to use that board very well. We were kind of educated on the problems of interest. We got to learn about the service, what their challenges were, what the opportunities for injecting technology. And for me, it was incredibly eye-opening. And that was kind of the first step. And then I won what I often call my first lottery ticket. The Scientific Advisory Board gig, it's a part-time job. So I did it in addition to my day job as a university professor. I did that for 4 years. And at the end of 4 years, I was getting ready to go back to my humdrum academic life, never being the same again for the excitement that I experienced with the Air Force. And then I won this lottery ticket, which is I was asked to be the United States Air Force chief scientist. Most fun job imaginable in the Pentagon. The chief scientist, there's no other job quite like it in the Pentagon. It's a role where you're working directly for the chief of staff and the secretary of the Air Force. And that was 4 years, frankly, of absolute bliss. And that was a full-time job. So I did that on leave from my university job.
Where were you at in the university?
So I was a faculty member at the University of Maryland. So I often joke that my major qualification for the chief scientist job was I was local. It's like, let's get him.
You were within proximity.
Yeah, no transportation. But it was a great time. I was brought on board. So the chief of staff of the Air Force was General John Jumper. He was absolutely focused on science and technology. And the secretary of the Air Force was Jim Roach, who still to this day is a close friend. Again, also really interested in science and technology. And the fun thing is that I had just come off, I'd done a study with the Scientific Advisory Board on low-cost space access. Now, it's something that we all talk about today, but this is, going back 5 years ago. And General Jumper specifically wanted to know if the Air Force could operate with a faster operational tempo. Could we launch things quickly? Could we get things into space responsibly? So, someone takes out a satellite, could we replenish it quickly? And so I spent a year on that study. I was one of the study members, and that got me the attention of the chief, who then asked me to come on board as the chief scientist.
Man, ahead of your time. I mean, this is before SpaceX. This is before, a Space Force existed.
Yes.
This is where the Air Force was playing a critical role in everything space for the United
And
States.
and the fun part is, you mentioned that was the first time I became aware of SpaceX. So in addition to touring every launch site imaginable, which was, an aerospace engineer's dream. I mean, we got to climb around the vehicle assembly building at Kennedy Space Center. We went to Wallops Island, went up to Kodiak Island in Alaska, went on the sea launch ship that Boeing had commissioned to do launches out in the Pacific. We also met with a number of small companies that at the time were ramping up to do space access. One of them was SpaceX. And I have to tell you, at the time, they were the most credible company that we met with.
Interesting.
Yes, fascinating study.
Interesting. So now you've positioned yourself, or not positioned yourself. You've gotten the opportunity to be the chief scientist within the Air Force.
Hmm.
The Air Force is extremely large.
Yeah.
How do you guys digest all of the different needs that the Air Force has in that capacity or in that role?
So, there are several tricks to it. One is, so I'll step back and tell you a little bit about the traditional role of the chief scientist, which is it almost always is someone taken from outside the Air Force for an outsider's perspective. Traditionally, it's always been someone from either a think tank or from a university, and it's term limited. So I did it under what's called the Intergovernment Personnel Act, called an IPA. I didn't give up my day job at the university. I just was on leave from the university. That was really important because when you take that job, you're going to be ruffling some feathers. If you do it correctly, you will be the person who explains sometimes that the emperor doesn't have any clothes. And so it could be career limiting if that were your full-time permanent job. So you come to that job with a sense of, frankly, fearlessness, that you can tell the truth, that you can identify problems and challenges without fear of reprisal. The other fun part about the job is you actually have very little direct authority. As the Air Force chief scientist, you don't really control anyone's budget. You have a very, very small staff. So the only authority that you have is associative authority. That is gaining the confidence of the senior leadership. So there's a personality element involved, which is learning what drives and motivates the senior leaders in the service, learning what keeps them up at night, and then trying to identify the connections to science and engineering solutions that will help them in their day job.
So let me get this straight. They come to you with their operational problems, right? Here's our Air Force set of challenges that we know today. How can we influence a change in this from a science and technology perspective? Do I have that kind of
Yes,
summarized?
although I would argue there's a bit more of an active element to it. So if you do the chief scientist job right, you travel around the Air Force and you learn about the issues. So I would go to different air bases, different commands, and I'd always look for how can something that the Air Force, how can something going on in the lab or something going on in industry help that part of the Air Force? You've got a problem with X. Well, hey, there's someone at the Air Force Research Lab who is working on a potential solution to that. You want to accomplish Y. Well, here's a possible way to do that based on research that's going on in industry.
So one of the things that I observed when I was over at DMEA is there was always a disconnect between the operator and the integrator. It sounds like your role is specifically designed to bridge that gap, to help solve that problem. So that way, when people are out in the field, they have the latest tech that they can integrate in to accomplish their mission needs. Am I
Yeah,
summarizing this?
that's a very good way to summarize it. Also, another part of that job that I took very seriously was to advocate for the role of science and engineering within the service. The Air Force is a service that was created out of science and technology. Um, Although I would also point out it's not just the technology, it's the operators of that technology. You need the airplanes, you need the pilots. But so the Air Force is very much a technology service. And so serving in that role, you're always looking for the how the technology can drive certain solutions to support national security.
And we're seeing that with an uptick of a lot of different deployments right now within the Air Force. NGAD being a great example, which is the next generation air dominance. I believe that's the
Yes.
acronym.
Yeah.
So you're seeing that influence, quite a bit now. Within this chief science role, do you believe that this was one of the springboards into your OSD role? And if so, what was your OSD role?
Oh, so absolutely. Serving as the Air Force chief scientist for, as I said, it was only 4 years, but it was 4 magical years. Completely changed my career trajectory. So actually, I'll tell you, when I finished up as chief scientist, I went back to my university job. And it's funny because my friend said, "Oh, you're going to be bored, silly. You're going to be miserable." I said, "No, no, no. It's going to be great. I've got all this knowledge, all this background. I know all these problems." Oh, my friends were right. I got to tell you, I wound up at the university. It's like, ugh. I remember one time coming home and just kind of sinking into the couch and telling my wife, I feel like I went from being in center field to sitting in the stands. And she said, "Oh, you're not sitting in the stands. You're in the parking lot, looking at the outside of the stadium." And so I was kind of very eager to get back to that. So I wound up spending about 3.5 years at the university. And then I wound up winning another lottery ticket, which was the Institute for Defense Analyses. It's a non-profit that runs think tanks.
IDA.
IDA, yeah, IDA. The president and CEO called me up and asked if I'd come and meet with them. And it's funny because I had been an adjunct, a research supporter at part time with IDA, and I thought he was calling to ask if I would support some new study that they were doing. Instead, he gave me the opportunity to run a think tank, a federally funded research development center, an FFRDC, that IDA operated that supports the White House.
Interesting.
It was really cool. So it's an organization called STIPI, the Science and Technology Policy Institute. It's a very small think tank, but it primarily supports the Office of Science Technology Policy in the White House. So working for the president's science advisor, supporting the president's council of advisors in science technology. And it's funny because when he approached me on that, um, it sounded like another dream job, but I'm going to admit I was very hesitant. And my wife, who is much smarter than me, is like, "Why are you hesitating? This sounds like so much fun." I said, "Well, I'm an aerospace engineer. My focus has been high-speed aerodynamics, propulsion. This is an organization that does everything. I mean, it's the whole of science across the government, everything from healthcare to energy, you name it." And my wife looked at me and said, "Yeah, so here's an opportunity to expand yourself." So, and she was right. So I took that job. I figured I'd maybe do it 3, 4 years, maybe 5 years. 7.5 years, I was still doing it. Had some great times. We it was very impactful. And then out of the blue, I got a phone call to come back to the Pentagon, and this time to come back in the role of Director of Defense Research and Engineering, overseeing modernization, essentially trying to get critical technologies into the defense ecosystem.
And so within that role of getting the critical technologies into the ecosystem, there had to have been a couple technology focus areas or passion areas for yourself. What were those?
So my research career has primarily been in high speed aerodynamics, the area that we call hypersonics. Hypersonics means flight in excess of about 5 times the speed of sound. So to put that in a little bit of perspective, most commercial airliners fly below the speed of sound, about zero point 0.7 or zero point 0.8 times the speed of sound. The speed of sound is Mach 1. Chuck Yeager broke the sound barrier in 1947 when he exceeded Mach 1. Fighter aircraft will sometimes go to Mach 2, twice the speed of sound. The fastest operational airplane that we've ever had was the SR-71 spy plane that flew at about 3 times the speed of sound. My field of research is beyond that. Mach 5, hypersonics, 5 or more times the speed of sound.
Now, what platforms are really in that space, right? Because I'm thinking to myself, if you're going faster than what the record is for human
Yeah.
flight, then there must not be a human in these kinds of systems, correct?
Well, it actually depends. So the record for a piloted aircraft in the atmosphere was held by an airplane called the X-15 rocket plane. 3 of them were built, 2 of them survive. One is sitting at the Air Force Museum in Dayton, the other is hanging off the ceiling of the Air and Space Museum. And one of the X-15 pilots, pilot by the name of Pete Knight, set the atmospheric flight record at Mach 6.7, so almost 7 times the speed of sound, back in the 1960s. Um, And so that's kind of the record right now. Now, there's also a part of hypersonic flight that relates to space flight, and that is every time a spacecraft comes back from space, it's entering the atmosphere and it's doing so at very high speed, high Mach number. So, for example, when the space shuttle entered the atmosphere coming in from low Earth orbit, it was traveling at roughly 25 times the speed of sound,
Okay.
Mach 25. That's hypersonic, but it was a glider. It was slowing down entering the atmosphere.
Okay.
Um, when the Apollo astronauts came back from the moon, they were traveling at almost 36 times the speed of sound. So Mach 36. So again, really hypersonic. Well, when we talk about hypersonics today, we're talking about a different application. We're talking primarily weapons. We're talking about unmanned things, cruise missiles. We're talking about gliders that have some weapons application. And that was my focus. So I come back to the Pentagon in 2019 and I'm raring to go on hypersonics. And there's been a long history of hypersonics starting and stopping. When I walked in, one of the big concerns we had was that China and Russia were making great advances in this field. And we, the United States, had allowed our lead to slip. In fact, by any metric that I could construct, we had fallen behind our peer competitors. And so I came in part to help solve that problem and get the US back in gear and competing in hypersonics.
And you also came back, if I remember correctly, during a time where the Pentagon had kind of done a evolution of the reporting structure, right? There was a split now of Office of Secretary of Defense for Research and Engineering,
Mhm.
focused in the research and engineering domain. And then there was Office of Secretary of Defense for Acquisition and Sustainment, which is a separate portion where they used to be combined.
Correct.
Now they have specific mission focus. And you were in the research and engineering portion of the Pentagon, correct?
Absolutely. So exactly your point. There was an Undersecretary of Defense for Acquisition, Technology, and Logistics, AT&L. And then Congress legislated that that be divided into the two pieces that you mentioned, acquisition and sustainment and research and engineering. And I came in under research and engineering. So that was a new office. And I thought that split was actually very well conceived at the time. And I'll explain. So if you go back in Pentagon history, there was a period of time when one of the most powerful positions in the Pentagon was the DDR&E, Director of Defense Research and Engineering. And over time, that position had been subsumed under acquisition. And for good reason at the time. The idea was there was a concern that research investments were too long term. They weren't focused on the needs of the services. So move it in under acquisition, and then your science and engineering enterprise is more focused on the service needs. Well, the pendulum tends to swing. And I think there was a realization that we'd gone too far, that research was so focused on acquisition that we were losing that long term horizon. So by breaking out research and engineering into a separate undersecretariat, I think that was really an important statement that no, we really need to be re-emphasizing the role and significance of scientific investments that the department makes. So that occurred, and in the first Trump administration, Undersecretary for Acquisition and Sustainment was the Honorable Ellen Lord, who very quickly became one of my heroes and one of my favorite colleagues in the building.
I couldn't
And
agree with you more, by the way.
Ellen is absolutely amazing. I would sit in meetings with Ellen, and just her command of information, her ability to change from subject to subject, absolutely unbelievable. And when I came in on day one, she was like, "You're even though you're in a different office, you're part of the team." And working with Ellen, her deputy Al Schaefer, who'd been a longtime friend, dating back to when I was Air Force Chief Scientist, Ellen and I had worked very closely. Kevin Fahey, who was the Assistant Secretary for Acquisition. It was just an amazing team. So I'll tell you a little bit more about the role that I came into in R&E. So when the R&E office was stood up, it was stood up with two pillars. One was science and technology, ST, and the other was advanced capabilities. We had Mitch Nikolic was the Director of Defense Research and Engineering for Science Technology. Jim Feist was the Director of Defense Research and Engineering for Advanced Capabilities. And then as part of that, the office was stood up with 11 what were then called assistant directors, each one overseeing a particular critical technology. So we had an assistant director for hypersonics and an assistant director for microelectronics, an assistant director for cyber, autonomy, network command control communication, directed energy, whole long list. About half of those folks were under Mitch in science technology, and about a half, and the other half were under Jim. I think there was the realization that the model wasn't quite working because first they weren't all working together. They were in different parts of the organization. They weren't all working together. They weren't kind of finding that connectivity. So I got brought in as a DDR&E for modernization, and I used to describe it as I was one ring to rule them all. All right, so we took all the assistant directors, we renamed them to principal directors, and they were all direct reports to me. And I have to tell you, it was a really magical time. I had this incredible team. The principal directors were just amazing people. I mean, I had folks like Nicole Petta overseeing microelectronics, Mike White on hypersonics. Um, it just this incredible list of capable people, and we were off and running. One of the things that I emphasized was, when I came in, I thought, my number one job was to make these principal directors successful. That's the job of a leader. Make the folks in your organization successful, and just running interference for them, and making sure that they were I used to call them the belly buttons for our critical technologies, working within the building, working outside the building, representing the importance of their individual technologies to the overall national security ecosystem.
So, with all of those different people kind of supporting your leadership, technologies move at different speeds, right? Not all of them are going to have, successes in a specific time frame. How did you balance each of those different pieces, knowing that some were lagging 6, 8, 10, years behind, even though they were making progress? It was just a challenge in and of itself. But also other technologies move rapidly. I mean, look at microelectronics, the way
Right.
that we know each other. I mean, there's a natural Moore's law that allows for advancements in technologies and then ultimately integration. How was that balance between, different moving speeds of technology under your leadership?
Yeah, no, great question. Exactly your point. Every one of our technologies was unique. Oh, there were some common threads. Um, you look at something like directed energy. All right, that was an example of a technology where it's always kind of in the future. It's always a few years out. We're almost going to get there. The exciting thing was, by the time I showed up back in the Pentagon, we were seeing some real successes in directed energy. And my principal director at the time was a gentleman named Tom Carr, who was phenomenal in that role because he was actually a skeptic of the technology. So he knew what it could do. He also knew he could also identify the hype. Um, but in the case of direct energy, it was pretty straightforward. You'd go through, it was pretty easy to figure out what the department was doing, what the services were doing, where their investments were being made, how to advance those investments, how to leverage, say, what the Navy was doing on behalf of the Army, what the Air Force was doing on behalf of the Navy. So that was pretty straightforward. I'll tell you the really challenging ones. Artificial intelligence. That was possibly our most difficult one. And I tell the story. We hired a new principal director for artificial intelligence. Jill Krisman was her name. Incredibly accomplished, credentialed leader in the field. And I think the first thing I told her to do was figure out what the department is doing in artificial intelligence. A couple of weeks go by, she shows up back in my office, says, "This is impossible." Everyone and their brother was claiming that they were doing something in artificial intelligence, and most had no clue what artificial intelligence even was. They just knew that they were going to use it. And we'd start these jokes that we're going to open an artificial intelligence store and sell cans of artificial intelligence to people needed to fix whatever project it was. So that was the challenge there. And if you tried to figure out, trying to get a handle of how much money were we spending on artificial intelligence, for example, it was almost impossible. So again, each technology kind of had its own challenges and opportunities.
Well, and it's interesting with the artificial intelligence example, specifically given when you started it and where we're at today. You're ahead of your time back then when artificial intelligence, like you said, was a topic people were talking about, couldn't really grasp where it fit. And coupling that, things like machine learning, for example, what is AI at the edge? All of these different types of pieces were buzzwords in a lot of different technology discussions, but how are they applicable to real world problems and even more into defense related
Right,
problems?
right, right,
How
right.
are we going to get artificial intelligence to help out the Air Force with all of these different types of systems that are operating in such unique capacities, some ranging service lives of 100 years, like the B-52.
Right.
Others that are state of the art, like the F-35. So many different platforms, all needing some influence of technology. And artificial intelligence was right at the beginning. So very interesting that was a spot that you guys were ahead of your time on.
Exactly. And the fun story about artificial intelligence is it for me it's one of the best advertisements for the investments that we make in defense science and technology. Because if you look at the precursors, the initial investments that were made in artificial intelligence, it actually came from the Department of Defense. It was investments from the service laboratories and investments from DARPA. And then honestly, we went through some funding troughs in artificial intelligence, and then we saw industry step up. And so by the time I showed up back in the Pentagon, industry was frankly way, way ahead of where we were in the Pentagon. And so we were looking at how do we claw back some of that knowledge from industry and apply it to some of the problems and challenges that we had. And I will tell you, there were some early missteps, but we also learned from those missteps. So I'll give you one of my favorite examples where you would apply artificial intelligence, and that is when we do intelligence gathering and we try to do intelligence analysis. And we've got roles for some of our intelligence analysts where essentially you take a 22-year-old fresh out of college, you sit him in a chair, you put him in front of a TV screen, you tell him to stare at that screen for 8 hours, staring at data that might be coming from some intelligence pipeline, and they're supposed to detect whether the big blob in the center of the screen is a minivan or a rock. And if it sits there for 8 hours and it doesn't move, it's probably a rock. And if it starts moving, it's a minivan, right?
Well, I'm already starting to think
Okay.
about fatigue here.
Exactly. It's mind numbing. And I remember visiting one of the Air Force facilities where we do this. And this is mind numbing. And the poor folks who were stuck doing this job, staring at a screen for hours and hours on end. Oh, so perfect role for machine learning to help identify and help the operator. So I was involved in evaluating an early implementation of one of those, and it turned out that that implementation actually made the job harder, not easier. And it was just the way it was implemented, and the information that was being provided to the operator, not asking the operator, "Hey, what do you actually need to make your life easier?" But we learned from those examples, and we were able to modify and develop new approaches, and now you're seeing those capabilities throughout the department. I'll tell you one of my other favorite examples of artificial intelligence. This is when I was in the OSD role. DARPA did an experiment where they had a machine learning system operating as a pilot in a mock dogfight against a human pilot. It was called the Alpha Dog Trials. The test got some criticism because, well, it was sort of artificial. It was a simulation. Yeah. But it was really an interesting experiment because what we found was the artificial intelligence system beat the human pilot every single time. Again, my pilot friends would say, well, it wasn't a real engagement. Yeah. And they're right. But it was interesting to explore how that system was beating the human pilot. And one of the things we immediately identified was the artificial intelligence system didn't have a self-preservation protocol. So it was doing things and maneuvering in ways that a human pilot would never maneuver because it was too risky.
It was a hesitation that a
Yes,
human would have. Yeah.
exactly. And I always remember that briefing the results to the then Deputy Secretary, Dave Norquist, and he kind of smiled and said, so what this tells us is we never want to program self-preservation into our artificial intelligence system. I said, yes, that's exactly right. But to me, it was very insightful because it showed us how if you pair artificial intelligence with the human operator, the combination of the two becomes incredibly powerful.
Well, and you see this pattern, I mean, with the way that artificial intelligence has done simulations like in chess, right? Where you have artificial intelligence beating grandmasters with less than 24 hours of learn time, but being able to take moves that are a little bit more risky than a human would do. Now, of course, amplifying that in a combat scenario, the artificial intelligence is still playing the game. It's still playing the game of winning this scenario versus where a human is saying, you know what, if I turn like this, I might lose my lunch. If I turn like this, I could crash. Maybe I don't want to do this. And your flight or flight kind of just kicks in where the artificial intelligence makes the calculated risk. No, I'm going to miss this objective by 30 meters, 10 meters, whatever it may be. I'm safe. I'll take the maneuver.
Yeah, exactly. I just a couple of days ago was listening to an example of an application of machine learning in the medical field that I thought had interesting analogies to defense. That is a model that was trained to look at EKGs and from an EKG detect certain heart diseases. Now, turns out it's very difficult to link an EKG to certain heart diseases. And when they've asked human doctors, when they've asked doctors to do this, they have a pretty high failure rate. Well, turns out you can train an artificial intelligence system that can look at an EKG and do a much, much better job of identifying potential heart disease. But now you combine that with the human, with the medical practitioner, and it becomes even more powerful. So you use the tool to help the practitioner identify behaviors, capabilities. And I think that's very applicable to what we can do in defense.
So as you've kind of accumulated all of these different knowledge bases
Yeah.
in technology over at OSD, um, it's kind of set up a new stage for you today. Why don't we talk about your role here in Purdue and what those passions continue to be as you support the current position you're in?
Absolutely. So I joined Purdue University about 2.5 years ago now as the inaugural president and CEO of something called the Purdue Applied Research Institute. And as the name suggests, our focus is on applied research, whereas universities typically primarily focus on basic research, foundational research. So the idea behind Parry, the reason Purdue University created Parry, was to essentially help bridge what we call that famous valley of death, which is the difficulty of getting something out of the laboratory into the hands of a user.
Like you mentioned at the very beginning, the hype that you saw with some of the technologies over at OSD, bridging that hype portion and actually translating it into something that was manufacturable or actually
Right.
executable.
Yeah, exactly, exactly. Now, I will step back and say there's a lot of discussion of that valley of death. My friend Jim Face likes to say it's not a valley of death; it's actually a mountain of death because there are a lot of opportunities and funding, especially funding available to do prototyping. Just relatively few of those prototypes make it into the hands of an end user. So Parry was set up in part to address that. It was also set up specifically to focus on national security research for the university. And let me explain. Purdue University, one of the great universities of the world, with a strong emphasis on engineering. One of the top engineering programs educates a tremendous number of incredibly well qualified engineers. Um, but Purdue has a particular affinity for supporting national security. The joke that our president likes to tell is if there weren't already a national defense university, we might rename Purdue University to the National Defense University. So, in that context, Purdue looked at its, various research programs and capabilities and opportunities, and realized that they didn't actually have a mechanism to do the more applied work, to do the more classified work. And so that's why our organization Parry was created. And I will say Purdue is not unique in this. I mean, there are other examples. Georgia Tech, for example, has the Georgia Tech Research Institute. It's been around for decades, incredibly well established reputation. Johns Hopkins has the Applied Physics Lab. MIT has MIT Lincoln Lab. So this was, not a new idea for Purdue, but something that Purdue hadn't done previously and made a significant investment.
So the Department of War has a spectrum of technology focus areas. We talked about it a second ago. Where does PARI kind of fall into these technology focus areas? Are there specific technologies that are highlighted as the most important? Because I mean, that's a wide range of stuff that we were talking about earlier.
It is. So in part, we built the portfolio at Pari based on the existing capabilities at Purdue University, matched to the high priority items for the department. So, for example, I talked about hypersonics. It's my own passion. Well, hypersonics is a key technology priority for the Department of War. It was just listed it's on the new list of technology priorities, scaled hypersonics. Purdue has a very, very long history of research in hypersonics. Incredible faculty members, a long list of students who have come out from the program, but also really impressive capabilities, test facilities, manufacturing facilities. And the other thing that we have at Purdue is a very close relationship with the U.S. Navy's facility in Crane, Indiana. NSWC Crane. It's an amazing Navy base. They focus on microelectronics, hypersonics, and we're joined at the hip with that organization. So hypersonics is one of the key areas at our organization. And if you will, I'll give you some details about all the exciting stuff we're doing in hypersonics. Second, microelectronics. So when I was in OSD, microelectronics was actually our very top priority. We were very concerned about the state of microelectronics for defense, and there are a number of I thought flashing warning lights, and where we were in microelectronics. And bottom line is, for a variety of reasons, we had fallen behind state of the art in defense microelectronics compared to the stuff that's available for commercial industry. Purdue also has a very long history of research in microelectronics, including some of the most impressive microelectronic manufacturing capabilities on any university campus. So microelectronics is an important part of our portfolio. And again, that's an area we work very closely with the Navy folks at NSWC Crane.
And it's a foundational technology,
Absolutely,
right?
absolutely.
So
It's critical to everything we do.
everything, absolutely. So you let in, and it got my curiosity going on some of the capabilities that you guys have. Let's start with this hypersonics piece, because as a microelectronics guy, I know about hypersonics on what I read in literature, and the very rare times I've been exposed to certain things. What sets Purdue apart with the capabilities you guys have established, and how is that contributing back to the Department of War?
So a couple of things that set Purdue apart. We have this robust ecosystem at Purdue focused on hypersonics. So let me explain some of the challenges that you have in designing, building, flying a hypersonic vehicle. Right. So when you're flying at hypersonic speeds, you're traveling so fast through the atmosphere that the skin temperature of your vehicle gets really hot. So you have to build a hypersonic vehicle out of high temperature materials, or protect it from those temperatures in some way. So materials and manufacturing is absolutely critical to a hypersonic vehicle. That's problem number one. Problem number two is propulsion. So a typical jet engine will not work at hypersonic speeds. So you need a different propulsion system. We typically think, if it's something called if we're going to be using oxygen from the atmosphere in our engine, then we use something called a scramjet, a supersonic combustion ramjet. It's a different type of engine. In some ways, it's the simplest engine you could ever imagine. In some ways, it's the most complicated engine you could ever imagine, but it's different than a traditional jet engine. So you need to focus on propulsion. Another problem with hypersonic flight, it's very, very difficult to simulate hypersonic flight on the ground. So you need unique test facilities that can do that. All right. At Purdue, we have all those. So one of the things that Purdue invested in for our organization, for Parry, is a facility we call the HARF. Purdue loves acronyms. The HARF is the Hypersonic Applied Research Facility.
This is why they get along with the government,
Oh,
by the way.
exactly. Purdue has more acronyms than the Department of War. It's great. I feel one of the reasons I feel so at home there. So the HARF was constructed specifically to do hypersonic test and evaluation. It has three critical parts. So one is a manufacturing center with state-of-the-art high-temperature materials manufacturing capability, mostly additive manufacturing for high-temperature metals, for ceramic materials. That's element number one.
Oh, wait.
Yeah.
The additive manufacturing piece is quite interesting.
Oh, it is.
So you're doing things like rapid prototyping and 3D printing of the materials?
Absolutely. Which again, is absolutely essential, we think, for hypersonics. And let me step back and explain that. So again, a hypersonic vehicle is flying under such conditions. It's going so fast, it's getting so hot that you need to use these advanced materials, but that can drive up the cost of the system, not just the cost of the material, but the cost of the manufacturing. So I'll give you an example. A hypersonic engine, one of those scramjet engines. We've known from work that was done by the U.S. Air Force, by the Air Force Research Lab, that the best designs of those engines do what's called active cooling. That means that the fuel, which is very cold, is circulating through the walls of the engine. It prevents the engine from melting as it's flying really fast, and also captures the heat that goes to the walls of the engine, and then delivers that heat back into the combustion chamber when the fuel burns. All right. So that means when you design that engine, you need to design that engine with cooling channels in the walls of the engine. The first versions of those engines were hand built. It was incredibly labor intensive and therefore very expensive. Now, with additive manufacturing techniques, we can build one of those engines with the cooling channels built into the walls. Right? It's one of the things that additive manufacturing does so well, and we've done that at Purdue. We've actually had students design and build one of these types of engines, and then test it in one of our laboratories.
Yeah, you're not constrained now by just the casting of a specific engine structure.
Exactly,
You're now
exactly.
able to have serpentine structures that overlay other serpentines where you wouldn't be able to cast something
Or
like that.
you'd be trying to machine things out and braze parts together. We put that all aside with additive techniques. Another thing that another area that additive manufacturing becomes really important. So if you think about a hypersonic vehicle, the nose of that vehicle at the very front of the vehicle is going to get much hotter than other parts of the vehicle. Leading edges, wingtips get really hot at hypersonic speeds. So you have to have different types of materials on the nose tip and the leading edge, as you do on most of the acreage, most of the surface of the vehicle. So blending those high temperature materials, making sure you've got the right material at the nose, the right material behind the nose, that becomes a challenge. Again, additive manufacturing makes that much, much more achievable. And so that's one of the important capabilities that we bring to bear. The other thing that we've got as part of that additive manufacturing center is a very extensive diagnostic capability, right? Because you build a part. So, for example, you build a part with cooling channels. Well, the cooling channels are inside the part. How do you know that they're actually in there the way you designed them? So we've got this detailed test and evaluation capability that once you make the part allows you to go back and see what it looks like. So that's element number one. Then element number two is this magnificent hypersonic wind tunnel that we've established in the HARF facility called HyPulse. Let me tell you a little bit about HyPulse. Um, it was designed by NASA in the 1960s to support the Apollo program. It was designed to simulate reentry conditions for an Apollo capsule. And then over the years, it was expanded, rebuilt, modified. And at some point, NASA gave that wind tunnel to industry, to a company up in Long Island that did hypersonic testing. And that company eventually got bought by another company that got bought by Northrop Grumman. So
The Northrop Grumman in Long Island.
no, Northrop Grumman in Long Island. So
Yeah.
now they own this wind tunnel, and honestly, they weren't using it very much.
Yep.
So
And,
they,
and and this facility's disbanded now. I think it's a movie scene or a movie set or something to
well,
that
actually,
effect.
parts of it, yeah, parts of it. So they were looking for a home for this wind tunnel, and so they donated it to Purdue University. Actually, technically, they sold it to the university for $10. So,
Not
but
a
it was
bad
a
deal.
donation, yeah.
Yeah.
And so first, thank you, Northrop Grumman. We love the tunnel. Um, Purdue paid to move the tunnel out to West Lafayette, Indiana, near the campus, built the HARF facility, part of the HARF facility around the tunnel, rebuilt it, rededicated it, modernized the instrumentation, and we're off and running. So it's an incredibly capable wind tunnel now. It can simulate conditions up to orbital reentry velocities. It can do different gases. It can simulate the chemistry that you experience when you're traveling at very high speeds. So we brought that online and we basically presented it now to the Department of War and said, okay, we've now added to the test capabilities of the United States of America. And then there's a third piece in our hypersonic facilities. Um, I'll take you back to some years back. Um, there was an idea that was conceived by a faculty member at Purdue by the name of Steve Schneider to build a particular type of wind tunnel called a quiet supersonic wind tunnel. Now, let me explain what that is. We had known for years, actually going back to the 1950s, that we put a model in a wind tunnel and measured some of its performance and compared that to actual flight data. There were some significant differences. One of the big differences is whenever an aircraft is flying through the atmosphere, the flow just on the surface of the vehicle starts out as smooth and laminar, but eventually becomes chaotic and turbulent. And when it becomes chaotic and turbulent is really important because it changes how hot the surface of the vehicle gets. It also changes how much drag, how much resistance to motion.
Yeah, I was just
that
thinking
they-
about the
yeah,
forces that would be on
exactly.
there.
It's
Yeah.
really important to know when flow goes from smooth and laminar to chaotic and turbulent. At lower speeds, we've got that nailed. You give me an airfoil, say on a commercial jetliner, I'll tell you exactly when the flow is laminar and when it goes turbulent. But at hypersonic speeds, at really high speeds, we don't understand the processes as well. And one of the realizations was, and we did measurements on the ground in wind tunnels, the flow tended to become turbulent much sooner than in actual flight. So that's a problem because your measurements obviously don't line up. Professor Schneider, came up with the idea of first he figured out why is it that wind tunnels give you a different answer than flight conditions. And he ultimately attributed to noise that you experience in the tunnel. You get disturbances in the tunnel. You think about it, you've got walls in the tunnel, you've got the effects of the walls on the flow inside the tunnel. A vehicle that's flying in the atmosphere isn't surrounded by a tunnel wall. It's a different scenario. So Steve came up with this idea of building a wind tunnel where you essentially remove every last disturbance possible. So you get back to real flight conditions. It was funded by the Air Force. The Air Force Research Lab, in particular, the Air Force Office of Scientific Research, bought into the idea and funded Steve to do this. Now, it's a real success story. The program manager at AFOSR was a gentleman by the name of John Schmisser, a distinguished hypersonic researcher on his own, and he believed in this concept. So he starts funding Steve Schneider to build the tunnel. They build it, they go to operate it. It doesn't work.
Oh
It's
man.
not quiet. And I will tell you that I think any other funding agency would have said, okay, well, we tried, you're done. But
Yeah.
AFOSR did not do that. AFOSR said, no, 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 we believe in the science. We'll get this right. And so they went through actually many years of nailing down why the concept wasn't quite working. And they ultimately figured out that there was a manufacturing flaw. So part of the wind tunnel that controls the flow hadn't been manufactured exactly to specifications. Essentially, there was a little lip inside that wind tunnel, and that was enough to throw off the performance. So when that was remanufactured, the tunnel started performing, and now it's a mainstay wind tunnel on the Purdue campus. It's called the Mach 6 Quiet Supersonic Wind Tunnel. Um, as an aside, when I was in OSD, when we learned that some of our peer competitor countries were building quiet supersonic wind tunnels to do this sorts of measurements, that really got my attention because that told me that some of our peer competitors understood some of the basic physics of high-speed flight. But back to Parry. So we're building a new quiet tunnel, but instead of Mach 6, this one will be Mach 8, and it will accommodate much, much larger models. And you might say, well, Mach 8, that's only two more than Mach 6. Well, it's a lot more difficult to do Mach 8 than it is to do Mach 6.
Well, when you gave the example of all of the different flight tests that had gone on and who held the world record, where it is today, I mean, just getting small portions of speed increases, it seemed like a monumental hurdle.
Absolutely.
So
Absolutely.
going from 6 to 8, I mean, it just, to me, it's blowing my mind thinking about going 8 times the speed of sound. I
Right.
mean, that is just a phenomenal feat in itself.
Well, I will put it in context, though. So the fastest human-made object that flew through an atmosphere was a Mach 65 times the speed of sound probe that we dropped into the atmosphere of Jupiter. It was a NASA probe. The fastest that we've ever had an object re-enter into Earth's atmosphere was about 41 times the speed of sound. That was another NASA probe, something called Stardust, that got some material from a comet. The fastest that a human being has flown in the atmosphere was Apollo 10. That was about 36 times the speed of sound. So compared to that, Mach 8, yeah, okay, that's doable. But you're absolutely right. When you're traveling at these speeds, the requirements for propulsion, materials, and an important difference, we're looking now at hypersonic systems, particularly for weapons applications that are not just entering the atmosphere quickly, but are flying for sustained distances, long distances through the atmosphere.
And I'm thinking about the remanufacturability of these, right? Having a one-off, that happens quite often in laboratory spaces, but being able to have something that is able to test over and over and over again for, like I said, the remanufacturability of different types of weapon systems is kind of the sweet spot here to ensure that industry is getting a bite of all of this different types of research.
Absolutely, absolutely. And when I look back, and the story of hypersonics is really in many ways a frustrating one because it's a field that the United States invented. We did all the foundational work. We developed the concepts. We did the early experiments. We had the early successes. And then we took our foot off the gas. I mean, we backed off from investments and we let peer competitors like Russia and China advance to the point where now they're ahead of us in this field. And if you look at some of the mistakes that I think we made, one was we allowed our test infrastructure to languish. We shut down wind tunnels. We stopped using wind tunnels. We also allowed our flight test capabilities to languish. So I'm happy to say that there have been significant investments in both those areas, both in wind tunnels and in flight tests, some from the government, but rather interestingly and exciting for me, many from industry as well.
And we're seeing that test infrastructures being a systemic challenge across the United States government. I mean, one of the areas that I'm knee deep in is the radiation test infrastructure,
Right.
specifically for microelectronics, right? So now knowing that hypersonics kind of plays in that same field where there was a dip in time where the United States, like you said, took their foot off the gas, and now is trying to reaccelerate to catch up with things is an interesting data point, which leads to the reference of microelectronics.
Yeah.
The second data point that you were
Right.
saying that the Perry Lab is focused on. Can you describe a little bit about what you're doing in microelectronics?
Sure. So first, I'm glad you talked about radiation hardening because we work very closely with our colleagues at Crane on that particular topic. Crane is the center of excellence for radiation hardening, and it is such a critical topic, which I think is as you allude to, we have not paid enough attention to, frankly. I had an experience where I was involved in the evaluate before I went back to the Pentagon in 2019. I was involved in the evaluation of a defense program that, frankly, had failed because we hadn't paid attention to the effects of radiation on the microelectronics. Basically, you had a contractor who built something, and then after the fact decided to say, "Oh, by the way, is it rad hard?" And they did the testing, like realized, "Oh crap, no, it's not going to work in the environment that we're flying it in." And then realized that going back and trying to redesign it would actually have been more expensive than starting over from scratch, which really stuck with me. And then we looked at, what are our test capabilities in the United States? I mean, you got to get in line if you want to do any sort of testing in that field. So really sensitive to that, working closely with Crane in that. There's a whole other issue though that I think is really important, and this caught my attention when I got back to the Pentagon in 2019 when we were working together. And I mentioned this earlier that defense had fallen behind state of the art in microelectronics. In some cases, we were using components that were one, two generations behind what was available on the open market. And it was in large measure because of decisions that had been made. And I like to say decisions that were made by, well-meaning patriotic Americans that had unintended consequences. We tended to go down the path of trusted foundries. And it made sense at the time. If we're going to put components in defense systems, then we want to make sure we know where those components are coming from. We know who's handling it. We make sure that every element of that microelectronic component is certified and verified and hasn't been tampered with. The problem with that model is defense is only like about a 2% of the microelectronics market. There are an awful lot more iPhones being built than there are F-35 fighter jets. So it's very hard to continue to make the investments on the defense side that the rest of the world, the rest of industry is making on the commercial side. And so quickly realized that the defense microelectronic components that we were using were orders of magnitude poorer in performance than what was being bought on the open market. And even worse, I would argue that we thought we were more secure, but in some cases we weren't secure because we were using old parts that gave adversaries a lot of time to get our parts and figure out what they were doing and reverse engineer them. So one of the big pushes that we had when we worked together in the building was getting the US defense industry back on the commercial curve. And, I mentioned I had a principal director who's overseeing that, Nicole Petta. She worked very closely with colleagues at Crane, folks like Matt Kay and Brett Hamilton, to ask, how do we nudge the U.S. back onto the commercial curve? How do we use the same stuff that everyone else is using, but at the same time make sure it's secure, make sure that there was no funny business, make sure that there was no tampering, and that's kind of the challenge.
So you opened up two interesting topics here. The first is the trusted foundry piece, right?
Mhm.
There's been a lot of discussion around how do we adapt as a defense department with secure electronics, right?
Right.
There's been a lot of kind of one-off sets of ideas, everything from zero trust to assurance to trusted foundries.
Yeah.
Two of the topics that have been introduced, and I'd love to get your opinion on this, is tiers of trust, having different layers of security, not being binary in one way. So, not saying that assurance isn't the right way, or the right, zero trust isn't the right way, or trusted foundry, but having an ecosystem of solutions and using them for specific applications. What's your perspective on
So
that?
I think you're exactly right. I've got colleagues who think the answer to everything is zero trust. I've got colleagues who think the answer to everything is trusted foundry, and the Venn diagrams don't intersect. Um, it has to be it has to be a range of capabilities. I will say this, I am a big fan of the zero trust approach. And that's something that we were pushing really hard because that lets you get on the commercial curve. But there are modifications, and there are challenges with zero trust. Validation and verification become really important. We've been working with our colleagues at Crane to address that issue, the validation verification issue. How do you actually do that for the entire department? They've got some really really clever ideas on how they would do that.
And I like the idea of tiers of trust because certain instances for certain systems will require a verification, validation, full kind of end to end evaluation because of the systems they're
Right,
going in.
right.
But certain times it doesn't require that. Sometimes it just needs, a first layer of security. And so understanding how that spectrum of options is available to those that are manufacturing, I think is highly critical.
Yeah, absolutely, absolutely, you're right. I find myself in many instances working on projects, looking at problems in which we actually are so concerned about security that security gets in the way of progress, right? And I can give you example after example where we were so enamored with being secret squirrel that we made it so difficult for us to access capabilities, and we made it so difficult for people to work together that we ultimately wound up thwarting our own best intentions. And so the idea of, yeah, let's do layers, let's do tiers. Not everything has to be classified at a certain level. Not everything has to have a certain level of security. I think you're exactly spot on.
And I love the passion that each of those different people that were working in these specific areas had for their specific niche of security, because each of those have helped to influence the options that we have available in secure electronics. So back to Perry.
Yeah.
Within that ecosystem, we talked about some of the close ties that you have with NSWC Crane and the secure electronic piece. What's the remainder of the portfolio that
Okay.
is within there?
So we do a number of other important areas. We have an infrastructure lab that looks at ways that you can rapidly build concrete structures. Now, this is where I step back and say, "Hey, I'm an aerodynamicist. I've spent my life figuring out how to move really quickly." When I first showed up at Purdue and found out part of their portfolio was building concrete structures, I'm like, "Really? They don't even move? That's about as boring as it gets." In fact, I've discovered it's an absolutely fascinating world, and dating back to the ancient Romans who developed concrete technologies. We have a laboratory. It's called the Bowen Laboratory at Purdue, and Parry utilizes Bowen Laboratory to look at applications of concrete technology specifically for the Department of Defense and related industries. The head of the laboratory is a professor by the name of Amit Varma. Professor Varma is kind of the world's leading expert on a particular type of reinforced concrete. And he's developed this technology which essentially replaces the conventional rebar in reinforced concrete with kind of a metal sandwich structure. So he builds concrete systems that kind of look like an ice cream sandwich. So you've got metal, and you got concrete inside, and you've got metal on the outside. It's a hybrid system. Um, it has many many advantages over traditional reinforced concrete. It's lower cost. It's more environmentally sound. It's more blast resistant. It's much easier to construct. You do preform slabs and trying to build do the rebar in situ, and therefore it has some wonderful defense applications. You want to build an aircraft shelter really quickly? Here's a way to do it. You want to build a missile silo really quickly? Here's a way to do it. It also has some implications. You're gonna store explosive materials. This is the way to do it because these metal structures handle explosion blast much better than traditional reinforced
Are
concrete.
they prefabricated before they're
Yes.
actually implemented? So it's almost like a set of Legos.
Exactly, exactly,
Okay.
exactly, exactly. And the fun part about it is you can kind of do the prefab depending on whatever project you're working on. You can do large prefabs, small prefabs. So again, it significantly reduces the time of manufacture because you're putting Legos together and then pouring the concrete. But it also simplifies the logistics significantly. So that's an area we're working in. And then as a spin-off for that, that same team is working on nuclear power. So there's been a resurgence of interest in nuclear power.
Oh, yeah.
Um, as an aside, one of my frustrations as an engineer is the United States had a plan for expanding our work in nuclear power going into the 1970s, and then we got derailed. And That to me, I think was one of the key bad decisions that we as a nation made. I mean, if we had gone to a nuclear system, if we'd gone to nuclear power, the world today would be a very different place. We'd be much less dependent on fossil fuels. We wouldn't even be talking about global warming, frankly. It wouldn't even be an issue, in my opinion. All right. So now, after the fact, 2026, there's a push once again for nuclear power. The Department of Defense is really interested in that. Small modular reactors, by the way, are becoming a focus. This is fun to see. When I was Air Force chief scientist, we had a push for small modular reactors, and we weren't quite there yet. So now, 20 years later, it's back and in a big way. Great way to power an airbase. Great way to provide power for a forward deployed unit. Um, it also has some other fun applications. Space, for example, nuclear power in space. If you're serious about operating on the moon, you need nuclear power. If you're serious about going to Mars, you need nuclear power. So, at any rate, spinning off from our work in infrastructure, Professor Varma and his team are also looking at infrastructure for these small nuclear power systems.
Oh, you're hitting a topic that I'm pretty passionate about here with the nuclear power. I got to see, I mean, even to this day, some of the struggles that are happening over at Diablo Canyon, which is over in the central coast of California, and the struggle that they've had to, keep that facility operational. And the point you just made, which it would be such a big change for the state of California with their rolling blackouts and
Right, right,
brownouts
right,
and the such,
right.
to have that energy capability, at their fingertips. So, and plus with all of the different exploration pieces that the world is interested in, having nuclear power beyond Earth is going to be highly critical.
Yeah,
So. With now Pari establishing itself as a center of excellence in multiple different areas,
right.
where do you see the biggest set of opportunities as we go forward in working with the Department of War?
So a couple of opportunities. Obviously, hypersonics is an area that we've invested very heavily in. Purdue University has put almost $50 million of its own money into hypersonics, and we've now come back to the department and said, okay, well, we heard the demand signal. We've made these investments. We want to be part of your hypersonics ecosystems. That one's very important. And I mentioned microelectronics. Obviously, another one where we're working. We've made some significant investments. We envision working very closely with the department. Infrastructure. I'll tell you another one that I think is a really important one that we're very much invested in. Energetic materials. That means explosives and rocket fuels, anything that basically burns and releases lots of energy. So Purdue, once again, has extensive capability in energetic materials. One of our faculty members, Professor Steve Bowden, is one of the recognized international experts in this field. Energetic materials is an interesting topic because, like some of the other technology areas that we've talked about, it's an area where the United States led and then allowed that lead to slip. If you look at the explosive materials that we're putting in most of our weapons today, it's using chemical formulations from the 1940s. The explosive materials that we're using haven't changed much since World War II. Now, we've developed more modern formulations. We, the United States, haven't implemented them. We're not using them. Our peer competitors have. The way we manufacture explosive materials also looks like something out of the 1940s. We haven't yet applied modern manufacturing techniques to to explosive materials and also rocket fuel. So the team at Purdue University has been working on this, and they do everything from designing the molecule, the energetic molecule, to figuring out how you build this in bulk, how you manufacture, large scale rockets, how you do, large scale warheads. The thing that Parry brings to the table is the application specifically to national security and being able to do things at the classified level with a controlled workforce. And so that's an area that we're looking in, and we're very bullish on that area. We think it's absolutely critical for the department, and it's also very timely. I mean, there's been a lot written about the number of weapons that we've been expending, giving, for example, we've been sending a lot of weapons to the Ukrainians to fight the Russians. That has depleted our stocks, and we've been pushing industry to ramp up production to replenish our stocks. Well, part of that is manufacturing the energetic materials, and so we see ourselves playing a critical role there as well.
You know, it's exciting to see all of the investments that are happening over at Purdue, in the Perry Lab. Your influence in running each of the different, what I would call pillars of success
Yeah.
within the organization. So I'm excited to see how this continues to not only advance from the academic applied research area, but also how it directly influences the Department of War as we continue driving forward as a nation.
Right.
This research is highly, highly critical to national security, and the focus that you guys are doing and the influence and the successes that are happening within this, not only on the applied research, but also the workforce piece is highly critical. So Mark, I
Yeah.
can't thank you enough for sitting down with me
Yeah.
today, having a discussion on all of these great advancements and continuing to watch your journey
Yeah.
as you continue making big impacts to our nation. So thank you very much.
Thanks so much for having me. I really enjoyed the conversation.